Hi, this is Andre. Today I'm going to talk about a topic that has been itching me for years and years. And I guess you have been affected by that too, if you're using Commodore computers. So today I'm going to talk about the VIA shift register bug. Stay tuned. The name VIA means Versatile Interface Adapter, and it's a very versatile chip indeed. It's got two 8-bit I/O ports with extra handshake lines, a timer, and a shift register that can be used to send or receive serial data. And it can generate CPU interrupts from a variety of conditions. It was one of the early 6502 related I/O chips and is used in many computers of the time, like the Commodore PET, the VIC-20, all the disk drives, the Apple II, or even the Vectrex arcade system and many others. And the best thing is, as opposed to other 8-bit hardware that you cannot get anymore today, only used or as a new old stock, the VIA is still in production today. A company called Western Design Center, founded by one of the designers of the 6502 and also of the VIA, Bill Mensch, is still around and selling the chips new. Having new chips is a great feature for anyone building retro computers, because otherwise you have to rely on auctioning sites or other shady sources. So I'm very happy to have this resource for my Commodore PET replicas that I've shown in other previous videos, or like this one. The Commodore PET has an IEEE 488 interface to talk to the disk drives. The cables for those interfaces were very expensive, so Commodore decided to replace the parallel IEEE bus with a serial bus when they designed the VIC-20 and the Commodore 64. And this bus is what I want to integrate into my next replica as well. And that is also where the shift register comes in. Commodore wanted to use the shift register to achieve speeds comparable to the IEEE 488 bus. But the infamous shift register bug of the VIA hit Commodore hard, and that's the reason why the VIC-20 and subsequently the Commodore 64 are so slow when accessing the disk drives. The IEEE 488 bus is about 8 to 10 times faster actually. Dave McMurtie from the Commodore International Historical Society channel, with whom I have cooperated in this video, has published a video on the historical side of the disk drive connections between the PET and the drives and the VIC-20 and the drives and so on. The link is in the description below. I recommend you watch it, but here I'll concentrate on the technical aspects instead. The VIA shift register is a synchronous shift register. That is, it uses a specific clock signal to shift bits in or out. It's not like an RS-232 serial communication, which doesn't need a clock signal. So the shift register has several modes. For example, you can free run the same byte over and over again continuously. And that is actually what the PET uses to create some sound using a piezo beeper. Just single 1-bit audio output with a piezo crystal. As a side note, listen to some of the more recent demos that really show off what you can do with that single beeper. But back to the communication. To send a byte from one VIA to another, you typically connect the sender shift register clock and data with the receiver shift register clock and data. The sender shifts out each bit on the data line while sending a pulse for each bit on the clock line, as you can see in this diagram. That is how Commodore planned to implement the VIC-20 and later Commodore 64 fast serial communication. Unfortunately, they found that the communication kept locking up and found out what the chip developers actually already knew. There's a bug in the shift register when shifting in or out under an external clock. When specific timing conditions are met, the VIA is missing a clock pulse coming in, thus missing a data bit. And you can see the description of the bug in the Synatec VIA datasheet. So the shift register bug happens when the shift register clock and the system clock of the receiving VIA are not synchronized. And that can happen anytime if the sender system clock and the receiver system clock are not synchronized, because all the oscillators have some variations and they ever so slightly move against each other, and then they end up in a situation where that bug happens, especially when you have two different clock domains, like you have the system clock of the computer and you have the system clock of the drive, and they are of course different and not synchronized, and so they move, and then the shift register bug happens. Commodore fixed the situation by sending out every bit separately using the CPU instead of the shift register. Doing this bit by bit is what makes the Commodore serial bus so slow. They finally created the 6526 CIA chip, probably know from the Commodore 64, that has a shift register that is not prone to that bug. The CIA is even used in the 1571 disk drive from Commodore for fast serial bus communication, even though most of the rest of the drive very much resembles the 1541, even using two VIAs like the 1541. And that fast communication is also what I want to implement in my PET clone. But there are no CIA 6526 available anymore, only those scavenged from Commodore 64 or 128 boards. So I want to use the VIA instead. That, you remember, we can still get new. So the shift register bug was present in these days, but is it still present in the new VIAs you get today? To see this, both me and Dave ran extensive tests with multiple versions of the VIA, old and new. My setup is using two Commodore PET clones. The Commodore PET has the shift register data and clock lines on the user port. So Dave and I collaborated to write two programs, one sending out 64K of data via the shift register on the user port, and the other one receiving this 64K of data on the user port and checking for error conditions. So in this code we're detecting two types of errors. First, we use a pseudo-random number generator on both sides to generate the same byte stream. So the receiver can easily detect bit flips that may have been occurring during the transfer. We're synchronizing both sides with a handshake line, and then we're only waiting for 256 iterations to see if the byte has been received by the shift register. If that hasn't happened, we assume that we have triggered the VIA shift register bug, which actually means that a shift pulse has gone missing. So we're detecting that as well, and this is the main purpose of that program. Because I don't have space for two real PET on my workbench, I decided to use two of my PET clones and connect their user ports appropriately. Note that in the test setup I also included a circuit that has been described to fix the issue. By the way, descriptions of the tests and the circuit are linked in the description below. The setup I've been using to develop the test programs for the shift register bug is that microPET here, which is a clone of the Commodore PET that has a VIA, and it has the shift register output on the user port, and those are the cables that connect to that patch board. And this is my other PET clone, also has the user port signals here, and here you can see how I patched them together, and there is the register that basically fixes the shift register bug. Personally, I have these 5 types of VIAs available for testing right now, and that's what I did. To run the tests, you start the receiving side It waits for the sender to signal that bytes are ready to be sent, and then the receiver tells the sender that it can actually send the byte, and it does it for every byte, so they two get synchronized. After the sender is done, it tells the receiver that the streak is done, and the receiver then prints a statistic of the detected errors. For each successfully received byte, it prints a dot, and for each error, it prints some error information. The shift register can be driven by different clock sources. The fastest one is using Phi2 system clock as a clock source, which would be 2 system clock periods per bit. But we found out that the results were all totally unreliable. We couldn't get anything good out of it. It's probably just a tad bit too fast for the receiver. So in the following, we're concentrating on the second way, which is using timer 2 as a clock source. And the fastest one is what we tested, is setting the timer to 0, which actually means n plus 2. Look at the data sheet. So it's 4 system clock cycles per bit. The other variations that we did is we tested with or without the schematic that is supposed to fix the shift register bug. So we could see if there is a problem without the shift register fix circuitry, if it's fixed by that circuitry. So how does the fix actually work? So here you can see the serial clock from the shift register, from the incoming shift data, is fed into that 7474 data register, which is clocked with phi 0, which is equivalent to phi 2 of that receiving VIA. And the output is fed into the CB1 input, which is the shift register clock input. And this little circuit makes sure that the shift register clock, when it comes at the VIA, is nowhere anywhere near the danger zone that actually triggers the shift register bug. That switch is indicating what you need to do if you also want to send. Then you have to get around that register, of course. And this here is a schematic how you can actually implement that little circuit with concrete parts. The description of that is also linked in the description below. Before we get to the results, and as not everyone has 2 pads, Dave McMurtie has also run the tests on 2 VIC-20s. And they have the shift register bits on the user port as well. So we'll let Dave show his results first.
The setup I'll be using to demonstrate the 6522 VIA shift register bug today is going to be 2 Commodore VIC-20s connected at the user port. The computer on the left is acting as the receiver, the computer on the right is acting as the sender. And if you look at the user port, you can see that the pins we have connected here are, get better light, CB1 going to CB1, CB2 going to CB2, PB0 going to PB0, and PB1 going to PB1. And it's the same over there. They just connect directly to each other.
The first test I'm doing is with a VIC-20 containing original MOS 6522 VIAs. I'll load the receiving code on the left, then I'll load the sending code over here on the right. Now I can run the receiving code. It's going to sit here and block until the sender begins sending data.
So the first test was with original MOS 6522 VIAs in the receiver. The second test, I swapped out WDC 6522s. And I actually swapped both of them just because Murphy's Law, I probably would have accidentally done the wrong one. So we'll test now with WDC 6522.
So here's the table that I made with all my test results. You can see it's all for the same setup. My micropad sending to my ultrapad, ultimate pad. The sender is always the same because the micropad has a PLCC type chip, which I only have this one. And I'm running the 64K test, 64K from the sender to the receiver, 64,000 bytes, 65,536 bytes, and checking for bit errors, which meaning bits that have flipped or are not incorrect, and shift errors. Here are the different types of receiver bit VIAs, and here are the different kind of test setups that I've used. What you can see here is, and I'm not going to talk about those, using the system clock Phi2 always gives very bad results. So let's ignore them for now. This is with the timer, used as shift register source, and there you see if the timer fix has been applied or not. And what you can see in the result is, for this Rockwell chip here, it's consistent that you have, and I made 3 runs for every setup. You see that we don't have any bit errors, we don't have any shift errors, only if we run with timer 2, so it has to be slow enough, and we have to have the shift clock fix in place. There's also 2 columns here. I'm going to talk about the right one only because the left one, due to the way the micropad worked, it has a very asymmetric Phi2 clock, which affects the timing of the shift register. So I actually, when I found out, and then I said, okay, let's look at some better results, I actually changed the programming on the logic chip in the micropad to create a symmetric system clock for the VIA for the sender, and those are these results here. So yeah, we see we need to fix for the Rockwell. Then we have the UM. I actually have to look up what company that is. Yeah, it's all again the same. Without the fix, it's a problem. With the fix, it's not a problem. It's fine. Cinetech, same results here. And now we're coming to the Western Design Center. And now you would think of, yeah, this is new, this should be working. And the first results were actually working, but that was with a very short, very asymmetric clock in the micropad. But then I changed to the symmetric system clock, and then I got errors again. So even the new Western Design Center chips do need this clock fix, and because this was kind of indicating there may be some other problems with this, maybe with the circuitry or with some stability, and you know, this is those chips are built for much higher speeds than the original one, so you may have some overshooting and other effects due to the very fast signal changes, up low, up down, and so on. So I tried some variations. I added small caps capacitor on the clock line, which actually removed the shift errors but introduced bit errors in addition. So then I added some more bypass caps on my breadboard, which introduced shift errors again. And then I got fed up and I said, okay, I connect both directly, and you have seen it in previous part of the video, where the two user ports of the two pet clones were connected directly without any kind of breadboard in between, and then we still have these error situations. To make sure we don't have any effects on other components on my pet clones, let's have a look at the schematics. And you can see here, this is the VIA chip, and here is the clock output, and here is the data output. And you can see the clock output basically directly goes to the user port, and it only is connected to another connector where nothing is connected, which is for the tape. And the shift register data output is connected directly to the user port, and the only other thing connected is an input, which has a high impedance. Should not do anything to that signal. Let's look at the same thing on the VIC-20. You can see here the port bits are directly connected to the user port. Also CB1 and CB2 pins are also directly connected to the user port, nothing else in between, so no interference from anything there on the board. So yes, even the Western Design Center, this variant needs the shift clock fix, and the other variant as well. I didn't do any further testing with this one, but the assumption is that this works the same. So in summary, we have all those results here, and yeah, I was kind of mildly shocked because this bug has been known for so long, almost 50 years now, and it's still not fixed, and that makes me sad. So finally, coming to an end, we see that basically all VIAs that we have this bug. My tests showed it, Dave tests shows them, and that is not what we have hoped for. There are variants out there that have the bug fixed, but unfortunately not the ones that we would have liked to have them fixed, namely the new ones. We sent out some questions to Western Design Center about that. So the bug is not described in the datasheet, so at least I assumed it fixed. The tests show that it probably isn't, or maybe isn't, but maybe it's because the chip is made for a higher frequency, so we have to probably modify our circuit accordingly. So Western Design Center has answered and asked for more time. But I want to get out that video right now, so I'll keep you posted, and let's see what they say. So what does that mean if you want to build a new solution that uses the shift register? If you're going to use those modes that are affected by the shift register bug, you basically have to include the shift clock fix in your schematic. Anyway, that's a real pity. The clock line is not bidirectional anymore. You have to have a separate I/O line that tells the direction of the communication and so on. So yeah, as I was not expecting this, I had to manually patch that into this prototype board for fast serial communication that I'm working on right now for my next pet replica. There are variants of the VIA out there that have that bug fixed. So if you have any of those variants, like the Rockwell 65CN02 or the ones from GTE, let us know. They must be super rare. Congratulations, you've made it that far. So coming to an end, I would like to thank Dave McMurtie from his Commodore International Historical Society YouTube channel for the great collaboration we had. And then, yeah, how did you like the technical deep dive? That was quite extensive this time. So let me know your comments down below. Thanks for watching, and see you next time. Here's my setup. You can see my pet replica, and it's got the fast serial board with the clock fix on top of it, and it is connected to this 1571 disk drive. And let's see how we can do fast serial communication. Let's start a little test program. I'm loading from parallel bus here, and then let me prepare the scope and start with the test program. What you see on the scope is the fast clock. This is a attention line, this is the slow clock, and this is the data. And you can see the data, the control data being sent via attention is sent with the slow clock, and all the data bytes have been sent with the fast clock. You only see single dip, which is an acknowledge on the data line. You can actually, you really have to zoom in to actually see how fast this communication can actually be if it wants to.